All right, welcome to the, I would call the very first real physics lecture for the semester for 1603. The purpose of this first lecture is to mainly outline all the quantities we'll be talking about from here on out, um, as well as we have to define basically everything. So a lot of this is written out very technically and fully in the notes. So I hope to keep this lecture somewhat short, but we know how that goes. Anyway, so this topic is, as a whole, will be known as kinematics, and more specifically, we're talking about we're only talking about one-dimensional kinematics right now. So stuff moving along a line, whether it be horizontal or vertical. We'll deal with both. Naturally, after we finish one-dimensional kinematics, we'll move on to two-dimensional, which you'll find working a problem in a two-dimensional sense is basically like working two one-dimensional problems. So even though this might seem easy at first to some of you, you really want to have a good grasp on it before we move on, because as I've said many times, the material throughout the semester will just keep building on itself. So if you get behind, you can get in some trouble fast. Okay, so with the math review, I believe I mentioned something about preferred direction, or we had to define everything with respect to something. This is of the utmost importance here. Typically, if we're doing a one-dimensional or two-dimensional physics topic, when you say the location of something, you kind of have to be really specific. Well, where is that with respect to what? 9 times out of 10, you're going to choose the origin. So in the XY plane, we're talking 0, 0. We also need, like I said, a preferred direction of motion. Typically, one chooses anything or any motion, any vector quantities to the right and up as positive. So that just means that anything left or down is negative. So you'll see how all that plays out once we start doing examples and all that. Okay, so my hands are tied a bit because being as this is an algebra-based course, all of the stuff we're talking about, the language of physics in general is calculus. So I can't really go into that because that's beyond the scope of this course. So it's almost more difficult to explain terminology and definitions in terms of just pure algebra as opposed to the calculus setting. But you can still do it. Okay, so when it comes to the things we can know about an object, so that's kind of the goal of physics at this level, is we're seeking to eventually be looking at how objects move and why, or how objects move in response to, eventually we'll get the forces and all that. And so this will be very practical because this is 99% of what you observe on a day-to-day basis. This course will cover how it works. Okay, so the first, in addition to mass of an object, the first thing we would probably want to keep track of for an object throughout a problem would be its location, or more specifically, we would call that the position of an object. Okay, so this might be, where is it? And again, we have to say it's here relative to something. So that's at most positions are going to be defined with respect to the origin. Okay, so mathematically, how these things look in the notes under the position section, you could call position X, but when we move to 2 and 3 dimensions, it might be X, Y, Z, or so on and so forth. In the one-dimensional case, we just constrain our object to move in a straight line, let's say in the horizontal. We could maybe describe the position of that particle or object through a variable X. If you haven't seen function notation in a long time, basically in the notes you see something like X parentheses T. What that is meaning is that the position X could be a function of time T. So if something's a function of something, all that means is that it, in of itself, the position, could change with time. So you won't see many cases where anything other than time will be in the parentheses. Most of our quantities will depend on time and be time dependent. But if you need to review on functions and function notation, I tried to put as much information in here as in the notes as I could. Okay, one of the first things when it comes to position that we'll need to cover is something that maybe in your colloquial speech you might use interchangeably, but in this course, these two words mean very different things. And so the two words I'm talking about, of course, are displacement and distance. So displacement, if you want to put a definition with a box around it, basically is if we look at the position of an object at some initial time and some final time, the displacement would be how far away the object is from where it started. Okay, I'm just letting that sink in a bit. Whereas the distance would be kind of what you probably mean when you say distance, the total distance covered by an object from time one to some later time. In order to kind of make this a little more real, I usually use an example of my walk to campus to demonstrate the difference between displacement and distance. I'm going to kind of be hand wavy with the actual distances, but it'll get the job done. So suppose I actually do live close to campus, so it's not that far away. Suppose I walk, well, back when I used to walk to school, say I walked 1 kilometer each way. That is, I leave my house, I go to school, teach, come home. Okay, so in a strict sense, my displacement once I get home, you ask, well, how far am I away from where I started? So my displacement for a round trip would be 0. I came back to where I was. But my distance would not be 0. Obviously, I covered some distance walking to and from school. So the displacement, because it's interested only in the beginning and final positions, my displacement is 0. My distance, however, would be, well, 1 plus 2, or 1 plus 1 equals 2. 2 kilometers. So I literally covered 2 kilometers of distance, but my displacement is 0. Okay. So I hope that kind of gives some light to what is meant by these two terms. Okay, so the progression we're going to follow in this lecture is we start basically with position, and then we ask the question, well, what if position changes with time? Can we define that or have something to say about it? And yes, of course. So we start with position. The next rung down the ladder would be the velocity. And I have to have another distinction here because a lot of people will use interchangeably velocity versus speed. They are similar, or more similar, I would guess, in distance and displacement, but they are fundamentally different. So first, we're going to define what the velocity is. So an object is said to have a velocity if the position of the object is changing with time. That's really it. From a calculus standpoint, that's where I would give you the real definition of the position, but here I'm restricted to only talk in terms of really what boils down to be averages, which is on the second page of the notes, the first thing we get to, where we have the velocity as a function of time is defined as the change in position over the change in time. So one thing I want to drill home quickly is anytime in this course, or the next course if you have that with me, anytime you see a delta, so that's that little triangle bit at the top, that's implying in and of itself a change. So it's always going to be delta x is going to be the final position minus the initial. It's always final minus initial. So if you saw delta q or something, you could go out on a limb and know that it's probably going to be q final minus q initial or something like that. Okay, so in our basic definition of velocity, the best I can do in here is an average. So what we do is we look at the starting and final positions and the starting and final times of that, and that'll tell us our average velocity. If you covered, say, 10 meters in 5 seconds, then you would have an average velocity of 2 meters per second. So 10 over 5. The units of some of these quantities, like velocity, it's made up from distance and time. So it will follow that the units for velocity will be meters per second, because those are the SI units of position and time. So when it comes to differentiating the velocity versus the speed, okay, so this is more having to be nitpicky about vectors versus scalars. So coming back to, if you say, hey, I'm going 20 meters per second, okay, so that is a speed. That's just a number. But if you say I'm going 20 meters per second that way, now we're talking about a vector, because we have both the speed and direction. So the speed is the magnitude of the velocity vector. So that's the big distinction there. Just to, when we come to defining, because we've defined the velocities and speed in terms of averages, I have to, again, I'm going back to the walk to and from school just to kind of illustrate this point. Strictly speaking, the average velocity is going to be dictated by the displacement, so delta x, which is x final minus x initial. So because my net on my route from home to school and back, my displacement was 0, so my average velocity also has to be 0. Just it's a consequence of that, which you can kind of rationale that. The first part of the trip I'm going that way, so my velocity is that way. Then when I'm coming home, my velocity is this way, so they kind of cancel out. So I have an average of 0 for the velocity. Now, the average speed, we really won't see this many times after this lecture, or maybe the first homework or something. The average speed, which I've given v sub average comma s, that's defined with respect to the distance. So you have average velocity, average speed. The average speed will be defined in terms of the distance d, which is, in my case, the 2 kilometers I travel. Okay, so just making up some numbers, let's say it takes me 20 minutes or 10 minutes to get to campus. Then my average speed, how long would it take me? Well, 10 minutes this way, 10 minutes back, and that 20. So that would give me an average speed of 2 kilometers per 20 minutes. I kind of purposely put this in here like this, so you would have to do a unit conversion to get it in meters per second. That works out to be about 1.6 or 1.7 meters per second. Okay, lastly, the thing we're going to talk about now is kind of the first bit of, or first variable that usually will not have associated with it some distinction between two words. So acceleration is acceleration. Okay, so we define, thinking about our ladder again. So we started with position. If the position is changing with time, we have a velocity. If the velocity is changing with time, now we have an acceleration. So the units for that, if we think back to position, units of position were meters, velocity was meter per second. So now with acceleration, we're talking about a change per unit time of a meter per second. So that's a meter per second, or meter per second squared. So that's the SI unit for acceleration. It's defined again as delta V over delta T. So some final velocity minus some initial velocity all over a time difference, T final minus T initial. Most of the times in problems, T initial is going to be 0 because you're assuming the problem starts when the problem starts. So the initial time would be 0. But there could be some times where that's not the case. Okay, so we have these 3 different parameters that we're going to be using to describe the motion of objects and how that motion might change with time. And so typically in class, I might derive these for you, especially in a calc class, I would derive these for you. We have a set of equations. We're talking about kinematics. So they are called the kinematic equations. Historically, there are 4 of them. One of them you never really use, so I kind of chuck it out. I don't use it. So at the end of the first 1D motion lecture, you'll find I've made them really large, hopefully to tell you how important they are. These are the what we call the kinematic equations. And so we have three. One we're going to call the position versus time or position time kinematic equation. The second one's a little shorter. It is the velocity time kinematic equation. And the last one's kind of an oddball. Later in the semester, you'll see where this actually comes from. But I usually refer to it as or my students usually do, as the funny square one because it has the VF squareds and VI squareds in there. So this is all I wanted to get through in this first lecture. So the next lecture will be going more in depth into how to use these equations, what they tell you, and why you might choose one over the other, depending on the type of problem you're doing. So that'll be where we pick up on the next lecture. Thank you.